नेटवर्क एनालिसिस में कोई भी सर्किट है तो उसको ऑपरेट करने के लिए हमको पावर चाहिए, पावर सोर्स। तो दो तरह के सोर्स का यूज करते हैं किसी सर्किट के अंदर, एक करंट सोर्स और दूसरा वोल्टेज सोर्स। तो लेट अस कंसीडर फर्स्ट इज करंट सोर्स। तो an ideal current source an ideal current source has infinite internal impedance, किसके, करंट सोर्स के, and supply a current independent of voltage across the terminals. कौन कौन terminals? There are two terminals. These terminals are A and B. These are the two terminals. These are the terminals. So इस टर्मिनल्स के वोल्टेज के ऊपर निर्भर नहीं करता है. इट इज graphical, or this is graphical. This is the x-axis, which is the voltage axis, and y-axis is the current axis. So this one is a VI characteristic. So in this VI characteristic, IS, current source is constant with respect to the voltage, whatever it voltage is. So the voltage across the terminals A and B must be infinite, which is not practically possible. कि practically ऐसा संभव है नहीं कि जो current source है उसके वोल्टेज इस तरह से इन्फिनिटी मिलेंगे, रेजिस्टेंस उसका वेरी नहीं करेगा, कुछ ना कुछ वेरी करता रहेगा. So what is the idea? That was the ideal case. तो practical case क्या है? Practical case is, this one is suppose a current source. This is IS. Here it is the impedance. There is some sort of the impedance over there. And these are the terminals. These terminals are A and B. And this is the source, impedance source. So if there is an impedance source, so what kind of the VI characteristic? It is voltage, here it is current. So this was the condition for ideal, it is the constant, and here it is the practical source. That is, on increase of voltage, there is there is a decrease in current. So how can you define if a load is connected? If a load is connected to the current terminal, then the potential across the terminals are given as, that is, here we have to add one load ZL. So current flow in this is IL. Here the current flow is IS, and this is the current flow is IS source. So what we find, this IL, potential across the load VAB, the potential across this is I load into ZL. This is ZL, and this is nothing but IS minus IL. This current is IS minus IL. This current. So this is ZS. This is ZS. So that is IS ZS minus IL ZS. So here it is IL is taken comma. So ZL plus ZS is equal to IS ZS. So IL is equal to IS ZS upon ZL plus ZS, or this is IS upon 1 plus ZL by ZS. 1 plus ZL by ZS. So this is equal to is when inside bracket 1 plus ZL upon ZS is equal to, this is 1. When it is possible, this ZS is, that is ZS is tends to infinity. If ZS is tends to infinity, then IL is equal to IS when ZS is infinity. Infinity. Infinity or sometimes infinitely large, that is sometimes we call infinitely large. So this one is the practical case of the current source, which is which is given as. So the ZS infinitely large, when we call it infinitely large. So ZS is approximate 100 times of ZL. If it is current source, so this one is 100 times of the load. So this is the current source. We can also have another kind of the source, that is called voltage source. The other is known as this is voltage source. Voltage source, an ideal voltage source has zero internal impedance and supplies out which is independent of current delivered by the generator or source. Generator or source. It can be draw as, this is the voltage, these are the terminals, this is voltage source, this can be expressed as, this is expressed as AC source, here it is was DC source, and the VI characteristic is something which is the current, and here it is VS, voltage, that is voltage is constant. But any zero internal impedance, that is if you say ZS is equal to 0, ZS is equal to 0, this is not possible. Any source has some finite impedance. The practical case is here it is, this is VS, this is VS voltage source, and here it is ZS, and these are the terminal points A, B. Here also this is the source, then there is ZS, this is the point A, B voltage. And the VI characteristic is, if it is IS, when the load increase, this is the ideal case, this value is decreasing, something like that. This is the voltage of the source, VS. This is VS. The internal resistance, the internal resistance or impedance must be zero. Internal impedance must be zero. This is not practically possible. This is not practically possible. That is, there is some finite value. Some finite value is there. If the load resistance ZL is connected, then what happens? This one is, we can say the circuit something like this. ZS, here it is source VS, and this is your load ZL is there. ZL is there. The current is flowing like this, IL. So V0 potential is IL ZL. IL is VS upon ZS plus ZL. This is the current, and multiply with this impedance. So it is the voltage. So Vs is equal to, this is 1 plus Zs by ZL. 1 plus Zs by ZL. So this V0 is equal to Vs only when Zs is equal to 0. Zs is equal to 0. Otherwise, V0 is equal to Vs minus Is Zs. V0 is equal to Is Zs. If Zs is not 0, so when Is is current in the circuit. Is is current in the circuit. So for good voltage source, for the good voltage source, this Zs is equal to very very small, and you can say 0.1 to 0.1% of ZL, 1 to 1. And this is used in case of the different positions and different part, that is, as current source, in case of the output section of hybrid circuit of transistor in electronics, and the voltage source circuit of transistor in output section, right? Voltage source is in input section of hybrid circuit of transistor of the transistor. So these are the voltage source, and the equivalent circuit can be drawn as this is input circuit, and here it is the output circuit. This is input section, here it is output section of the, here you can see this is B, this is C, this is E. So CE configuration, CE configuration. So this part is voltage source, and this part is current source. It means in voltage source the impedance is very small, and in current source the impedance is very high. So these are the basic concept of the current source and voltage source. Now comes to the very famous law, and all of you know that the famous law is your Kirchhoff's law. Kirchhoff's law. So there are two Kirchhoff's law. One is Kirchhoff's current law, that is known as KCL, and here it is Kirchhoff's voltage law. This is KVL and KCL. The first law for the circuit, that is, suppose this is the point, and here it is the current coming to the point, here it is receding. So you can say incoming current, and here it is outgoing current. This is I1, here it is I2, this is I3, I4, I5, I1, I2. So you can see at the given junction, the algebraic sum of currents at node is 0. So we can, this I is equal to 1 to 5, here I is equal to 0. That is I1 plus I2 minus I3 minus I4 minus I5 is equal to 0. So this is dq1 by dt plus dq2 by dt minus dq3 by dt minus dq4 by dt minus dq5 by dt is equal to 0. So we can have dq by dt q1 plus q2 minus q3 minus q4 minus q5 is equal to 0. So del q is 0 at the node, So this is also known as conservation of charge. Conservation of charge. Because this conservation of charge is delta q is 0 at the node point. This is your node point. So this one is the first, that is known as Kirchhoff current law. Now Kirchhoff voltage law, we can express this is, suppose this is the impedance Z1, here impedance Z2, this is impedance Z3, this is impedance Z4, this is impedance Z5, this is the source, and here it is. This is V1, here Z1S source, and this one is Z1, this is Z2, this is Z3, this is Z4, Z5, Z2S, and here it is V2. So the current is flowing in the clockwise direction, and the current in this is I1, here it is I2, and this current is I3. This is mesh 1, this is mesh 2, and this is mesh 3. There are 3 meshes. So the KBL is in the closed, in the closed mesh, the algebraic sum of the potential drop across the impedances and voltage sources are 0. The mesh equations are written as, this is I1 Z11 plus I2 Z22 plus I3 Z, this is 12 13 is equal to V1. Here it is I2 Z21 plus, sorry, this is I1. This is I2 Z22, this is I3 Z23 is equal to V2, and I1 Z31 plus I2 Z32 plus I3 Z33 is equal to V3. So these are three currents and three mesh. Here this equation is mesh 1, this is mesh 2, and this equation is in mesh 3. This can be written as I1, I2, I3. Here it is Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33, and this is V1, V2, V3. These are the matrix equation. The same matrix equation can also be expressed as this is I, this is I, here it is Z is equal to P. This is the matrix equation. The current impedance, this is the current component, this is the impedance, and here it is voltage source, where the most important factor is Z11. What is Z11? Z11 will be all sum of all the impedances in mesh 1, that is Z1A source plus Z1 plus Z2. This one is Z11. Z12 is equal to Z21 is equal to minus Z2 is common to mesh 1 and 2. Z13 is equal to Z31 is equal to 0. That is common to mesh 1 and 3. That is no impedance. Z22 is equal to Z2 plus Z3 plus Z4. That is sum of all the impedances in mesh 2. Z23 is equal to Z32 is equal to minus Z3. That is common to mesh 1 and 2 and 3. And Z33 is equal to Z4 plus Z5 plus Z2S. That is sum of all the impedances in mesh 3. And then V1 is voltage V1, V2 is 0, and V3 is V2. So these are the values of the different components in the mesh equation. These equations can be solved. These equations can be solved. For example, determinant of Z, that is Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33. This is the determinant. And this determinant can be expressed mod Z. And on the basis of this determinant, that is very easily you can calculate from anywhere, we can find out the current by using Cramer's law. So using this Cramer's law, Cramer's rule, the currents I1, I2 and I3 can be expressed as I1 is equal to V1, V2, V3, Z12, Z13, Z22, Z23, Z32, Z33. The whole is divided by Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33. These one. So what we have, the simple way is just the first column for determination of I1, we have to replace this voltage, first column voltage impedance, this impedance Z1, Z21, Z31 by the voltage V1, V2 and V3. Similarly, we can determine I2. I2 is Z11, Z21, Z31, and the second column is replaced by voltage. It is V1, V2, V3, and third column remains same. Third column remains same, and this one is Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33. This one is. And if you interested to write I3 in the same way, so what we have to, this determinant, the third column is replaced by voltage. The third column is replaced by voltage, that is Z11, Z12, V1. Here it is Z21, Z22, V2. This is Z31, Z32, V3. And this. And whole thing is divided by this Z11, Z12, Z13, Z21, Z22, Z23, Z31, Z32, Z33. This one. Or we can also express as R. I1 can be expressed as, this one is C11 V1 plus C21 V2 plus C31 V3 divided by mod Z. this can be expressed C11 by mod Z into V1 plus C21 by mod Z V2 plus C31 mod Z V3. Similarly, we can express I2 second current, that is C12 upon mod Z V1 plus C22 mod Z V2 plus C32 mod Z V3, and I3 is C13 mod Z V1 plus C23 V2 plus C33 mod Z V3, where C are the cofactor of the determinant, cofactor of the determinants. So these are the techniques, these are the basic techniques through which we can express the current. And if you can have the value of current, then the potential can be calculated by potential drop across that particular component, that is multiply impedance into current. So potential drop. So we can analyze any circuit of any number of mesh. What is the advantage of the matrix mechanism? Because we can take, here it is the matrix 3 cross 3 because there are 3 mesh. We can increase the matrix order, that is m cross n, if there is a need to do all these things. So this one is the Cramer's rule, and this is the Kirchhoff's law, which is very important and used to discuss frequently. Now, in order to make how simple this law is, so we can take the examples. When we'll solve this, then the things will be more clear. So take the example. This is example 1. This is the example 1, and the example 1 is find out the current in the network. Which kind of the network is? The network is given as, suppose this one is the resistance. Here it is the resistance, and this is the resistance, and this is the supply voltage. This voltage is positive, negative, and here it is another supply voltage. So this kind of a simple network, the voltage is 10 volt, this is 10 ohm, here it is 5 ohm, and this is 20 ohm, and this is 5 volt. So there are two currents, I1, and here it is I2. There are two currents because there are two networks. So there are two current and there are two networks. So the solution is the mesh equations. Mesh equations can be written as I1 Z11, I2 Z12 is equal to V1. Here it is I1 Z21 plus I2 Z22 is equal to V2. This one is the mesh equation, where Z11 total resistance in the loop 1. So the total resistance of the loop 1 is 10 ohm plus 5 ohm. So this is 15 ohm. And Z12 is equal to Z21, that is minus 5 ohm. And Z22 is 5 plus 20. So this is 25 ohm. This is 25 ohm. V1, V1 is 10 volt and V2 is 5 volt. These are the potentials. This is 10 volt and this is 5 volt potentials are there. So the equation, determinant equation, that is current I1 C11 upon Z V1 plus this is C21 upon mod Z V2. So mod Z is Z11, Z12, Z21, Z22. This is the determinant. Its value is Z11 is 15. Z11 is 15. Z12 is minus 5. Z21 is minus 5. And Z22 is 25. So this determinant, that is mod value of this determinant, is 15 into 25 minus 5 minus 5. So this value is 375 minus 25, that is 350. Z value is 350. So by substituting this value, that is I1, and the cofactor, you see the cofactor of C11 is 25. So this is 25 upon 350, and the voltage is V1. V1 is 10 volt. V1 is 10 volt. And minus C21. C21, the cofactor is minus 5. So this is minus 5 by 350 into the potential is 5 volt. So it is 5. So this value is 250 upon 350 minus 25 by 350. 250. So this is 225 by 350. That is 0.642 ampere. This one is I1. This one is I. The current I1, the current I2 is this I2 is equal to C12 upon Z V1 plus C22 by Z V2. So C12, this one is C12, that is minus 5 into 10 upon 350 plus C22 is 15 by 5 by 350. So the value is minus 50 upon 350 plus this is 75 350. So this value is 25 by 350. So this value is 0.071 ampere. So the answer is I1 is, this is 0.642 ampere and I2 is 0.071 ampere. So these are the two currents and these currents can be solved through the other method also. Through the other method means uh, we have the traditional method that you have applied in your 10+2 standard, how to solve this one is, but we use here the Cramer's rule. Now we take the example 2. The example 2, that is another example, by taking the circuit, you see the circuit is something like this is 2 ohm resistance. This resistance is connected with a capacitance which is connected with the 1 ohm resistance, and here it is a cell. This is 12-volt cell connected with another resistance, that is 2 ohm resistance. Another cell is here connected with the resistance. So this is 2 ohm resistance. Here it is 3 ohm resistance, and here we connect a inductor L of 10 millihenry. These points are connected. This is S, this is A, this is B point, 2 points. So it may connected as per requirement. This is switch. This is switch. Switch is connected to A and switch is connected to B. So in this given, there are 3 mesh. So the first is find out the currents in the given circuit. That is, here the current is I1, this current is I2, and this current is I3. So basically this is the mesh 1, this is mesh 2, and this is mesh 3. There are 3 mesh equations. And the points, this point is A and this point is B. This point is B. So when switch S is connected to A, switch S is connected to A, potential difference across A and B, VAB, potential difference across VAB, first case. Second, when switch S is connected to B, switch S is connected to B, then current I3, find the current I3, and steady state, energy stored in it, time. Time when current in 3 ohm resistance is half of original, that is I3. So This is the question. This is the question. So what we have to do in the circuit, there are three mesh equation, and when we connect, first case, when switch A is connected to A, this is connected to A. So this is disconnected. B is disconnected. So the lower part is disconnected. So no current is flowing. So circuit is, when this is connected, then the circuit configuration is something like this is. So this is 2 ohm. This is 2 ohm, 12 volt, 3 ohm. Sorry, 2. This is 2 ohm. This is 2 ohm. Here it is. The voltage is 3 volt. This is 3 volt. So this is the current in I1. Here it is current I2, and there are basically two mesh. In this case, this is the capacitor. The capacitor is providing infinite impedance for the DC supply. Therefore, this part is disconnected. That is no need of this capacitor and 1 ohm resistance in this circuit. So basically, mesh equations are I1 Z12 plus I2 Z, sorry, this is I11. 12 is equal to V1. Sorry, this is I1 Z21 plus I2 Z22 is equal to V2. These are the two mesh equations, and the corresponding current that is I1. I1 is equal to C11 mod Z V1 plus C21 mod Z V2. So what is this mod Z? Mod Z is Z11, means Z11 is the current total value of the resistances, that is 4. Here minus 2, here minus 2, and this one is 2 plus 2, again this is the 4. This is the 4. So its value is 4 into 4 minus 2 into minus 2. So this is 16 minus 4, that is 12. So the I1 value is C11, this value and this value. So it is 4 into 12 upon 12, 4 into 12 upon 12 minus 2 upon 12 into 3. So this is 4 minus this is 4, this is the 3 1 by 4.5, that is 3.5 ampere I1. This current is I1. And the I2 is equal to, C12 upon Z V1 plus C22 upon Z V2. So C12, this is C12, this value. So it is minus 2 into V1. V1 is 12. 12, that is 12. minus C12, C22, C12 is this one, C22 is, it is 4, 4 by 12 into 3, 4 by 12 into 3. So this value is positive. So this 12, 12 cancel, it is minus 2, and this is plus 1. 4, the 4 is cancelled, this is 1, this is minus 1 ampere. This is minus 1 ampere. So the potential difference is, the potential difference is the potential difference across A to B is VAB. VAB is I2 R2 minus V2. That is, I2 is minus 1, R2 is 2, minus 3. So this is minus 2 minus 3, that is minus 5 volt. This is minus 5 volt. So in case 1, I1 is equal to 3.5 ampere, I2 is equal to minus 1 ampere, and VAB is equal to minus 5 volt. This one. Case 2, when switch S is connected to B, when switch S is connected to B, so this circuit is S to B. Here it is the cell. This is the resistance of 2 ohm. This one is 10 millihenry. Here it is 3 ohm, and this case 3 volt. So if it is connected, then at the steady state is the steady state current is I3, and this I3 is equal to V by R. V is 3 volt, and this R is 2 plus 5. 2 plus 3 is 5. So 3 by 5 ohm, 0.6 ampere. This is 0.6 ampere is the current. Now when it is connected to the circuit L, so in L circuit, the growth time for half of the original. How much time? Now current in LR circuit is expressed as this I is equal to I naught 1 minus ER by L into T. This is. So we have to find out the time when this I is equal to I naught by 2. This is 1 minus E minus R. Minus R is given. that is you are taking R by L, okay, this is T. So here these cancel. So what find 1 by 2 is equal to 1 minus E R L by T. So e raised to the power minus R L by T is equal to, this is 1 by 2. So 1 minus 1 by 2, that is 1 by 2. Or this is 1 upon E R L by T is equal to 2. So this is 2 is equal to E raised to the power R L by T. So T is equal to L by R log E base 2. L is 10 millihenry, 10 into 10 to the power minus 3. This is 5 total resistance into 0.693. So this is 2, this is 6, this is 8, this is 13 into 10 to the power minus 3. That is 1.386 millisecond, the time. So this time is 1.386 millisecond be the answer, under which this one is the given. So we are solving these two equations, and these two equations, these two examples are very important examples. I just want to explain the clarity of the Cramer's rule in the network. That is, first you formulate the mesh equation, then determinant of the form, and then the corresponding current. And if you want to calculate the potential, so multiply the impedance with the current potential. And then the second part is, sometimes it is also called as the extra part that we have to calculate. So here in case of the circuit, we have included capacitance as well as inductance. So the capacitance part, as it is DC, it is not applicable here. So that part is deleted itself. And in case of inductor, the half, that is the decay of the current, peak value is 0.6 and the decay value is half of the 0.6. So I naught upon 2, and from that equation, that is we have the T, and this T is equal to log base E2 L over R. So from this point we can calculate, that is 1.386 millisecond. So these are the two examples. That examples are very important for us. And